This December will mark 50 years since the last human set foot on the moon. With the Artemis program, NASA plans to break this streak, sending both manned and unmanned missions to the lunar surface. To enhance operational flexibility, NASA desires a device capable of supplying power and communications to other assets, expanding their range and capabilities. As part of the 2022 NASA Rascal competition, the B team created a conceptual design for a portable utility pallet, or PUP, featuring Samsung 35E battery cells to supply over 125 kilowatt hours at 60% depth of discharge to other assets, laser-based communication using NASA LCRD technology to supply well in excess of 50 megabits per second communications with a lunar gateway, origami folding solar panels to maximize the size of the solar array against its stored volume, along with other features to enhance the capabilities of the PUP. Due to budget and physical constraints, the team's prototype focuses on implementing the self-leveling function via the independently adjustable legs, which provides more stability on uneven terrain and clearance over small obstacles.
1. Launch. The pump will launch sometime around 2028 on a rocket headed for the moon contained with a dampener to prevent any damage from the intensity of the launch. 2. Cruise. The rocket will follow its course to the moon with the pup on board. 3. Landing and unloading. Once the rocket lands on the moon, the pup will be carefully unloaded either by personnel on the moon or through the use of machinery designed to transport the pup. 4. Relocation. The pup will be relocated to the desired location for deployment where it will then be placed for setup.
Deployment. The pup will deploy its solar panels and ensure all systems are functioning properly. Logistical support. The pup will then begin its primary mission of providing logistical support through the distribution of power to other assets and providing communications for astronauts and robots are part of the Artemis missions. Relocation. At some point during its 10 years on the moon, the pup can be relocated after retracting all deployables. Redeployment. The pup can then be redeployed at a new location to continue its mission. Decommissioning. Once it has completed its 10-year mission, the pup can be decommissioned, retracting its deployables and powering off, or it can continue operation until a later date.
The pup comes in at a final weight of 1673 kilograms with a volume of just under 8 cubic meters. The batteries aboard the pup are comprised of Samsung 35E battery cells, which produce over 250 kilowatt hours when fully charged. The power system is able to provide enough power to the instrumentation on board the pup, such as the ECAM timepick, which is a micrometeoroid detector, as well as the necessary communications dish, which provides 50 megabits per second upload to the lunar gateway. The battery also works in conjunction with the software and computer subsystem to deploy and retract the telescoping legs and the boom. A folding origami solar array solar panel is connected to the telescoping boom to provide all the necessary recharging to the secondary batteries on board the pup.
The prototype of the pup will feature two of the key components of the full-scale model, as mentioned before, the self-leveling function of the independently adjustable legs, and the solar panel power production that is a primary mission of the pup. These were to be the components built and tested as a demonstration of the intended full-scale design.
The original leg design features a pulley system that used wires wrapped around a spool to extend and retract the legs. As the legs are retracted, the legs all face upwards. When deploying the legs, each leg folds out and down along with support tubes. Then the wire is pulled by a motor which deploys each leg. Each leg is able to be adjusted depending on the terrain of the pup. An Elegoo Mega microcontroller running Arduino IDE software is utilized as a central control unit of the system. An infrared receiver is connected to the Elegoo such that commands can be received via infrared remote. An inertial measurement unit is also wired to the Elegoo to provide the system with real-time gyroscopic data. 5 servo motors connected to the Elegoo are then used to run the mechanical systems, one for each leg and one for the boom. The remote allows for the total manual and automatic control over each servo motor. Based on user input, the motors can operate individually or simultaneously while deploying and retracting. Additionally, the user can choose a deployment mode where the Elegoo uses gyroscopic data to determine how far each leg should be extended in order to maintain a level orientation. This mode proves useful when deploying the pup on rough, uneven terrain.
Each of the 4 motors are connected to a spool containing high-strength fishing line which extends and retracts the legs autonomously using an infrared receiver and Arduino configuration. The 4 individual servos are in charge of independently raising and lowering each leg until a final level position is reached. An additional servo is also solely responsible for the deployment and retraction of the telescoping boom. Additionally, 32 miniature solar panels are mounted to the panels on top of the boom to produce around 200 watts of energy in direct sunlight, which directly powers the battery pack and Arduino.
The development plan was to purchase the materials, coordinate with the machine shop to cut the aluminum, build each main subassembly, and integrate the subassemblies. The leg and the telescoping boom pulleys are each made of nesting PVC pipes and string. The pieces of the solar array pedals interface together with hinges to facilitate the origami movement. The main structure of the pup is made of multi-purpose aluminum fastened together with corner brackets. Epoxy will be used to mount the solar cells onto the solar array. We only spent around $740, which is a small portion of our total allotted budget. The main structure, aluminum, occupies the largest percentage of the cost at 38%.
The original plan for testing kept in mind both the goals that the full-scale version of the pup would seek to accomplish, while also adjusting the expected results to the scaled-down prototype. The primary testing goals were to determine the power production and compare it to the analysis, and ensure that the self-leveling system of the legs could handle uneven terrains replicated as closely as possible to the lunar conditions.
The initial plan for the legs included the pulley, but the rack and pinion mechanism was better suited for the legs. The string in the pulley created friction that hindered the leg movement. We lubricated the strings and tried fishing line as an alternative material, but neither solution was optimal. The rack and pinion was working well with the boom, so this mechanism was replicated on a smaller scale for the legs. The 45-degree leg mounts were replaced with vertical leg mounts so that the racks and the servos were aligned to operate in the same direction of motion. Several failures for the 45-degree leg mounts led to the final leg mount design that could withstand the forces imposed by the legs. The hinges from the solar panels were removed such that the panels are in a fixed horizontal position. The hinges added a lot of unnecessary weight onto the structure and was taxing on the system. Lastly, the solar panels did not pack fully into the pup's body due to the limited internal volume in a scaled-down model. A better method to pack the pup prototype for transportation is to fully retract the boom and have the solar array sit flush with the pup's top panel. During construction, there needed to be a lot of testing for the 3D printed parts. All of the parts have been redesigned due to either the part not working as intended or the parts being too mechanically weak to withstand the forces expected. Throughout the trial and error, the major parts that were redesigned were the leg mounts, previously mentioned, the pinion gears that connected to the servos, feet, and the mount for the servo controlling the boom. It was also during construction where we realized new 3D printed parts were needed, like the stabilizing mount for the legs and the boom mount at the bottom of the pup.
The development of the first pup prototype was rife with many unexpected challenges that slowed development and led to late-stage design alterations. As a result, the unit presented in this video will be further refined into the product that will be presented on Design Day. The final prototype will contain many improvements from the current version, the most notable including recut body panels that fit with fewer gaps and overlaps, revised 3D printed components to ensure smooth mechanical functionality, and a uniform color scheme to tie everything together. Thank you.